Have you ever had to deal with old scripts that stop working because the software has changed? By the end of this video, you will know exactly how to avoid that problem once and for all. Hi, I'm Marcos Morgan. I've been doing bioinformatics for over 2 decades. Today, I'll show you how to build a stable software infrastructure for your analysis using Docker containers. Let's start from the beginning. What is a Docker image? An image is a bundle of software that includes not just the main program, but everything it needs to run. That means you can run software built for Mac, on Linux or Windows, and it just works. We download images using the docker pull command. So let's try samtools, which I always found tricky to download and install. So to download the samtools, we have to go to Docker Hub, look for the biocontainer samtool image, and then here in the tags, we go to this command here, we just copy that. And now in our command line, where we have Docker installed, copy that command, run it. It starts to download the image. So once that is done, we go to the images and you see that biocontainer samtools is installed. I had it installed before, so that's the difference, but you will have it there. So now that we have the image, we would like to run it, and we use it with this command, just called Docker, and we send run and the image. In this case, since the container has been developed with this Linux chip, and we have this other one, we need to add that specification. You might need to do that in your project. So we go ahead and add this platform specification here. So, and as you can see, that worked, but we were not asking anything to the container, so it just opened it and then closed. So let's call samtools here, tools. When we do that, it just runs samtools, which gives you this help version, and then it exits. You can also open an interactive session of your image, and we do it with the following command. So we need to add this IT parameter here, and we ask to have the bash program. So when we launch that, you see that we have this user that changed. It's no longer my name from this computer. We are inside that container or image. So now we are inside the container. Try typing samtool again to confirm it's working. And these running instances of these images is what we refer to the containers. So if we run again here, samtools, you have the same parameters or commands. So now if we go back to the Docker desktop and we move from the images to actually the containers, we find that there is actually this container running that is coming from this biocontainer samtool image. It's always given this funny combination of names, and this is the ID of that container that is running. So far so good. We have these images that are a bundle of somewhere that we can download. Each time we call these images, we have the so-called containers that are these images actually being run. But sometimes you need a specific setup. For instance, you want to have R plus a topGO package for ontology analysis. And if there is no ready image, you need to build your own one. So let's do that. We'll start with the Rocker tidyverse platform. So I have this Rocket tidyverse image already pulled, and I will be accessing and creating a container. And within this container, I will go into R and I will install the library for the topGO package. So I enter R, we are there, and ask to use this library topGO. It says that there is no such library, so we need to install that package, and we do it the way that is explained in the bioconductor repository. So we'll give it this command, and this will start installing the package. This can take a while, and I will spare you these few minutes. So once the program finishes installing the topGO library, we can inspect the container. So this is the container that is actually being run. It's called REMI Hayam, and we can inspect actually this container. And if we go here to the files, You can see that some of them have been modified, and these are the things that have been added to that container. So once we have installed this topGO package or whatever package in your modified container, the idea here is that you can save this container as a new image. And we do this with the following command. We call Docker, use this command commit. We give the name of the modified container, and it will be saved as this image. That is the Rocker tidyverse, that was the base, and I identify it with topGO. So if we do that, we created that image. And now if we go to the images, we see this Rocker tidyverse with this tag topGO2. So now let's try to relaunch this new image and see whether we have our topGO library in there. So we use the same command, run it, and then the platform, and this time we are calling the image that we just generated, and we run this interactively. So we are inside the new container generated from the image. We go to R, and now if we write library topGO, we see that the library is there. So we are good. And we see here that it's also installed. So far so good. We have these new images, and at a certain point we would like to store them somehow to share it with someone, or in case our environment changes, we can call that image and use it out of the box. So how do we save these images? One thing is to create a file with the whole image. So to save our topGO2 image, we use the command save. We specify the tar file that we want to create, and from where we wanted to create, that is our new topGO2 image. So we run that. It takes a while, but once it's done, we can go to this Docker for bio folder over here and see that we have there our file with our image. Okay, now let's try to call this image back. So we delete this image that we just generated because we already have it saved, and I will re-upload it from file using this command image load and the name of the file. So there it downloaded the image, and we have it with this name, and again it appears again in our topGO2 image repository, and you see that it's revived. Docker sort of remembers if it has seen something similar, so that's why this is not being updated. The problem with this approach, however, is that these images can be very heavy, in the order of a couple of gigas. The alternative way of doing this is to create a so-called Dockerfile, where we just specify what commands you need to do to recreate that image. So let me show you how that works. So we just create this text file where we said, okay, from this Rocker base image, open it and run this command, and we call R, and we download our topGO library. This is the Docker file, and now we need to run it, and we do it this way. So we use this command, that is docker build, then we'll tag it topGO3 just to differentiate it from the other ones, and we will use this topGO2 Docker file that I just showed you, that is in this folder over here. If we launch that, it will start making that image. So now in our Docker desktop we have our topGO3 image ready to go. So now if we go to that topGO image that we just generated, we can go to R, and we can see that the topGO library is there ready to go. So now that you have your containers, you can generate it, update it, save them as images, distribute it. The question remains, okay, how do you use it? In particular, how do you give access to those containers to your data in a computer? We do this using the so-called volumes, and I'll show you exactly how to upload those volumes to your container so that your container can make use of them. So for example, let's say that I want to do some mapping of a FASTA file, and I have this folder with the FASTA file and FASTA file and the transcriptome to which I can map it. So how do I provide access to a container to this folder? So we run the following command. Again, we have docker run the platform, And now we have this parameter that is the one, the V, that loads the volume. Here we're telling this load this volume to the same volume inside the container. And then with this W parameter, we say start working from that container. So if we go ahead, launch this thing, this will start running. And actually we see this minimap2 container that is actually running over there. So now if we access actually that container, you see that it's running, doing its job. If we go to the files, we have this one that has been added and actually is giving the path to this mapping. So it's like copying exactly that information, and you see that this volume has these FASTQ files and this FASTA file, and inside the container is creating this SAM file. The next concept that is important to have clear is how do you allocate resources to your jobs within Docker. So probably when you start running these things go slow, they never finish running, and this is probably because you haven't assigned enough CPUs or RAM to the Docker container. So let me show you how to do that. For example, here we can see if we go to the stats, we see we are using 3 CPUs, that's the 300% and uncertain amount of memory. Imagine if you want to run many of these in parallel, you will need to have multiple CPUs. To modify that, we go here and resources, and within these resources you can increase the CPUs allocated to Docker, the memory, etc, etc. Okay, that's it for today. I show you how to download images, how to modify them, how to create new containers, how to save them, share them. Then we talk a little bit about how to use these containers with different volumes and how to allocate resources to Docker so that your program actually runs. If you like the content like this, please subscribe to the channel. And if you want to see an implementation of an RNA-seq pipeline using Docker, please check the video now on screen, and I will see you there.